What I wanted to do today is talk about inelastic spectra and pretty much take you on a tour of the different aspects of inelastic spectra. I have many slides, and so only because this is something that I've been working on and I've put a lot of ideas together. So what I like to do is introduce you to the different concepts in inelastic spectra. So I want to make sure that I just give you guys a little insight into what the experience that I've had with inelastic spectra. This is kind of my perspective on what we're doing, and I really want to emphasize this perspective, that it's important, because oftentimes I personally get bogged down into the details of, even just a single degree of freedom system or a multiple degree of freedom with the structures, the ground motions, the geotechnical modeling. But what we have to keep in mind is that we're really trying to focus on an individual building, but then even bigger about what we're doing with structural analysis. And so today I'm going to take you down one little path of the inelastic spectra, but the point of what we're doing with inelastic spectra is to gain insight into the structural behavior, which is of a bigger model, which is to give you insight into the behavior of an actual structure. The objective for today is to define the inelastic spectra and talk about terminology, and also just really gain an understanding of the different components in the process. It's not, we're used to seeing the spectrum as a graph, but you'll see that there's just so many different aspects that you have to get into your brain for really understanding what you see in these graphs and what the implications are, but then also to understand the process so that you can develop inelastic spectra and to understand what kind of inelastic spectra you want to do. And so it's really important that you understand the stages of what are you trying to do? Is a single degree of freedom elastic model enough of what we're trying to do, or do we need to go beyond that? And what is involved in going beyond that? And then at the end, what is the meaning of what we've achieved once we've developed, a much more refined model of a single degree of freedom system? And so my goal today is to just throw a lot of different ideas into your head that I want you to think about. We're not going to answer all the questions today, but I kind of want you to walk away with more questions than answers, things that you didn't know you had to think about as you're developing the inelastic spectra. Understand what all the different components, and start thinking about how these components fit into what you're trying to do. And so that then you can ask educated questions of the model, educated questions of yourself, and really have a conversation beyond just looking at the data, but understanding what's behind the data and why did you make such assumptions, and what are the assumptions and choices that you have to make along the way. I figured this is a really good skill set for everybody. As we move forward, hopefully inelastic spectra are going to become much more part of a discussion in looking at the models that we're doing. So I really kind of wanted to plant a few seeds in you guys' knowledge bank. Okay? So the outline is I've got about 87 slides, but I kind of want to fly through them. Also, again, I want to start the conversation. I have this many slides because I always like to have everything in one package. But again, if we get through a few, if we get through many, we can skip some, and to kind of, again, give you little screenshots of what's out there. We're going to start with elastic response versus design spectra, just the definition of those and how they're computed, because you need to know that to then go on to looking at inelastic response spectra. And I'll give you some little demonstrations, and I feel like the little videos are helpful in just picturing. I'm very much of a visual person, and so picturing what these different single degree of freedom systems are doing. Once we understand the elastic and inelastic spectra, then we get into 2D response. And what are the questions? What does it mean when you're in the 2D world for an elastic model? And then adding the complication or interesting issues with the inelastic response spectra. I have developed a tool that a long time ago that I used to compute inelastic spectra, but my focus is not to show you how to use this tool, but I want you to think about how to build the model in this tool. The tool automates everything for you, but you have to make the modeling decisions along the way. There's a lot of pull down menus there, and so I want you to think about what you're going to put into every one of them. You don't just take the defaults that I've given you, or if you take the defaults, at least understand why and what were your options. Okay? We jump right away to response spectra. And again, this is a nice, big, long definition in the slide. And so the point of the response spectrum is to give you an idea, not just of the amplitude of your earthquake, but also to give you an idea of the frequency content. And based on that, that frequency content is going to give you information about the response of your structure. So in one plot, you could really identify right away, it tells you everything about how your building is going to behave. And just in one simple figure. And as we go deeper down the rabbit hole today, to really keep in mind that sometimes even this simple elastic response spectrum provides 97% of the insight. And so what we're trying to do is what additional insight can we make into our model. Response spectrum is typically associated with a ground motion itself, while a design spectrum is associated with the site and what's expected in shaking in your structure. Very important to keep the two concepts separate, and we're going to mainly be focusing on the response spectrum. Different structures with different periods have different response to the different ground motions. And the main difference between, oftentimes people ask you, why are you doing a response spectrum? Why not just a Fourier spectrum? A response spectrum takes into account the damping. And damping has a way of almost coupling the modes between, even if the main frequency is at one period range, it will actually affect your structure that is in a different period range, or at least close enough. So that's why we're looking at response spectrum and not Fourier analysis. Response spectrum is of a simple single degree of freedom system, and the main properties are damping, and then stiffness and mass, which are put together into a fundamental period or frequency. And this is something I wanted to make sure that we're all starting at the same place, but oftentimes we take this definition for granted. In the way we compute it is you pretty much write a loop. And so I want you to start thinking about, this is very easy to do in OpenSeas, that you just build single degree of freedom systems and you just vary different damping ratios. Typically, we're only looking at 5%, but most of the time we're actually looking at a lot more damping levels, or you pick a particular one. We pick a certain ground motion or a set of ground motions, and then we just literally run a time history response analysis on that single degree of freedom system. We pull out the maximum response, maximum absolute value of the response, and we plot it as a function of period. And so from that, we get the spectral displacement. Typically in elastic response spectra, we then take that displacement and convert it into pseudo acceleration and pseudo velocity. It's important that we're looking at these pseudo quantities. We're not looking at the total acceleration, because what we're really interested in, first of all, structural engineers, is responses associated with deformation. And two is because you don't have all this kinetic energy and damping energy that's really difficult to then separate. So what we're looking at is the PSA, it's the pseudospectral acceleration that we compute from our displacement response spectrum. Why am I making a big deal? Because this is going to come into play when we look at inelastic response. When we're looking at inelastic response, we have to step back and look at displacement. Here's a fun way to plot. It's an interesting way of plotting a response spectrum, which is really the ideal. It's called the tripartite plot, where because of this relationship between the period, the velocity, and the acceleration, you can actually plot all three of them into one plot where the horizontal is the period, and then you've got the different angles for acceleration, velocity, and displacement response spectrum. You'll often see this, and it's kind of a neat way of looking at this plot. I wanted to show you a quick demonstration of this is all in OpenSeas. This is what we're actually doing when we're doing our single degree of freedom analyses. I do it with a lot of them, and what you see on the top right-hand side is the response. Same ground motion, different periods and characteristics. Here I'm just showing you as a height. You get, different maxima, different frequency content, and it almost looks like, the higher frequency ones, the stiffer structures, and not necessarily stiffness because there's also mass associated with it. You almost don't see the deformations, which is an important feature of stiff structures. Just because you don't see the deformations doesn't mean that they're not there, and that maybe forces may actually be more important. So that was the demonstration there, just to give you an idea. What we often do is we take elastic response spectra and we compare them to the design spectra for your site. And remember, I told you before, you've got a ground motion, but you also have at a certain site a certain level for which structures are designed. And so it's neat with elastic response spectra when you plot those against the design spectrum. And so this is a project that we had done after the South Napa earthquake. And we're just looking at comparing, these are the spectra in the two directions, the H1 and the H2, so handled individually, and you compare them to the design spectrum. And by doing that comparison, you could see, hey, look at this, structures that are in the period range between maybe 0.1 second to half a second are expected to exceed the design level, while structures in the other period ranges are not expected to see it. But for the same earthquake, you're at a different site. Now you may have a different design spectrum as well as a different response spectrum. And therefore now, in this case, structures in this period range are affected. And then, maybe you're far enough that you're so far away from your design spectrum. So it's interesting, and I'm focusing on this because I think it's important to understand what the response spectra are doing, and especially when we start off with something that we're familiar with, such as an elastic spectrum. And so that's it. That's easy. Elastic response spectra are relatively easy. When you get into inelastic response spectra, now you've got, you're looking at the inelastic response of your structure. You've got energy dissipation. You've got a yielding in your system, as well as you've got energy dissipation. That leads to a difference in response just purely based on strength. So you may have the same initial properties, and so your elastic response spectrum will give you the same values, while if you actually subject it and do a nonlinear analysis, you'll see that you have different maximum displacements depending on the strength of your structure. I'm going to give you a little demonstration of that. I'm big on demonstration. So now what I have is, again, still in 1D, and these are structures that right now the two models are overlaid, where you've got the elastic and the inelastic structure right on top of the other, okay? And so you don't really see the difference. But as soon as the amplitude goes up, and you see these are different periods and different strengths, you'll see that as now we go into the inelastic response, you start seeing yielding. And your overall response is different. And so here you just, we have a soft story effect in this system here. But really to show you, hey, look at what's going on. Not only different strengths, but also different periods will have different responses between elastic and inelastic. And another important feature, and I will address that later, is that at the end, you may end up with residual displacements. And the residual displacements are important. We are able to capture those even in a single degree of freedom system. So that's, I think, is pretty cool. But now things get interesting. People call it complicated. I think it gets interesting. How are we going to idealize that single degree of freedom system? And we're used to, and we've seen a lot of this when you just do a the simplest resolution is an elastoplastic system. You've got elastic response until you yield a maximum strength, and then you've got zero tangent stiffness, and you keep on cycling. And it's similar to the behavior that I showed you before. And so now you've got to take into account what is the envelope. It's not just an elastic stiffness, but how are you going to model this envelope? How do you convert a curve that is curvilinear like this into a bilinear response, elastoperfectly plastic, or more interesting, as I will show you in the next slides. You also need to take into account how are you going to model the loading and the reloading behavior, as well as the strength and stiffness degradation over time because of cycling. So now the problem has gotten more interesting and more challenging. So, and this is something that I want your brain to start thinking about. Well, it really depends on the type of structure that we're modeling. This is a neat example from Chopra's textbook. Is actually a great resource to start looking at inelastic response. And here's on the top, you see the forces. In an elastoperfectly plastic system, the deformation's at the top. In the middle, we look at forces. And the forces, pretty much, they cap at the yield strength. And so now we can't plot spectral accelerations anymore. We actually have to look at displacement. And so what we're used to looking at pseudo PSA response spectra, when we're talking about inelastic response spectra, we're always talking about deformation measures. And I will show you how there's a lot of different metrics that we can look at. Also, the maximum strength demands that you could achieve, that you would need for certain deformation requirements. The other interesting thing that you have to take into account and think about in the inelastic response is how many times do you go into the plastic range. And so if you look at this plot, which is an elastic system and then weaker and weaker, so as we take the yield strength is equal to the elastic strength, but now if we reduce our yield strength, we expect our structure to go more and more inelastic. Well, what's interesting is you get more and more residual displacement. Your displacement peaks are in completely different places. Here was a negative, here was positive. And also the yield count is something that may be important to your structure. It really depends on your structural system and whether that's a metric that's important, but it is something that you can track. And you'll notice here, the weaker the structure, the more it's going to go into the nonlinear response. And that's very important because the weaker the structure, the more ductile you need to make it, because the ductility demands are going to go up. The inelastic deformations are going to go up. And so that's when it comes in, and now we build these inelastic response spectra. You've got your model, and so this is from Chopra's book, therefore this is a simple elastic perfectly plastic system. So we've only really made one additional parameter, which is your yield strength. And now you can really see by just changing one parameter, we get very different responses. And the difference in responses really depends on the period of your structure. And you can plot different quantities, and it's very important to think about what quantities and what type of response spectra do you want to look at. So this one here is purely deformations. It's the maximum displacement. On the left is divided by the ground displacement, or you can normalize it with respect to the elastic displacement. So now you're taking the amplitude of your structure out, the amplitude of your earthquake out, because you're normalizing it by the maximum elastic displacement. And so you'll look at these and you'll find these normalized deformations. And look at what's interesting here, and you'll see it here as well, is short period structures are very, very sensitive to displacements. They get really, really large displacements once you have yielding. And it's important because that's a very different type of response than these more flexible structures. And you could almost see it in the little demonstration that I gave you, but in the little demonstration, see this displacement values here, this is logarithmic. These displacement values are much lower than these displacement values for the more flexible structures. But if you normalize it, now you see, hey, wait a minute, my demands are, I expect my lower period structures to be much more affected and more problematic during inelastic response. And so these are two types of inelastic response spectra that you can develop. Another set is when you bring in the definition of ductility. And why is ductility important? Well, ductility is a good metric of damage, and it's really pretty much the ratio of your maximum displacement divided by the yield displacement. So if your ductility is less than 1, you're elastic. If it's greater than 1, you're inelastic. This is something we all know and take for granted, but it's really, really important in evaluating structures and the information that we get from our single degree of freedom system. The other thing to take into account when you go into ductility greater than 1 is that now you're dealing with residual displacements as well. And that's a measure that needs to be kept in mind as you do your analysis or evaluate your structural performance. And so now that we've defined ductility, now you're going to find these ductility demand spectra, which is pretty much the step. We take what we had before, which was our maximum displacement demand, but instead of dividing it by our elastic displacement demand, we divide it by our displacement capacity. Okay, and so now this is proportional to, if you have a very short period structure, the deformation capacity is going to be small compared to a long period structure. And so it's a much better normalization now of these amplitudes. But again, if we plot, these are the different strengths. So Ry, remember I had told you before, Fy is the ratio of the yield strength to the elastic demand. And so the inverse is, the weaker the structure, the higher the R ratio is. And so as you weaken your structure, your ductility demands go up. And so it's very important when we're looking at inelastic structures to make sure at the design end to provide that ductility capacity. So the ductility level is really important in what we're doing, and we're computing our inelastic spectra, because that's what we're trying to communicate to the designer or to our client. The inverse of that is, and this is a really almost the most popular spectra, is the constant ductility spectra. Now, because typically in design, especially when you relate it to displacement-based design, but even at performance levels, right? When you think about a ductility of 8, then you know that something is about to collapse. Lower ductility levels, you can almost relate to different performance levels. So you want something to remain almost elastic. So maybe you want to design your structure to reach a ductility level of 1.5. If you have, reinforced concrete columns, it's just a bridge, maybe you might be happier, you're fine with going to higher ductility levels. And therefore, what this constant ductility spectrum tells you, and it's pretty much an interpolation of these curves moved over, so this is just data processing, as were all these other, it's still one analysis, and it really depends on how you process the output, is I'm going to tell you, hey, I want to design my structure to reach a ductility demand of 4, because that's a good place to be. And it has a period of maybe, 3 seconds. Well, you go here, you take your curve, you look at your period, and you find out, okay, I have to define my structure to have an R factor, quote unquote, a ratio of my yield capacity to either the elastic capacity or the weight. It really depends on how you plot this, of 0.2. And that's really what the objective of these constant ductility spectra are. These are very much for design. And then the ones on the left-hand side are more for evaluation. If you have a strength of your structure, tell me what the performance is going to be. And so that's, with the same data, you can be communicating two very different concepts. If I'm an analyst, maybe I'm interested in the one on the left, because that tells me what the demands are. If I'm a designer, I want the one on the right, which tells me for what capacity do I need to design the strength when I know I can provide a certain level of ductility. Okay? So this is, to me, it's the most important concept that took me a little bit of time to get to in looking at constant ductility spectra, or the different inelastic spectra, because everybody talks about it and how we can compute them, but what is the real meaning and what are they communicating to us? So if you walk away with this today, I'm more than happy. Anything beyond this is extra, which of course I've got a lot more going into that. So the question at this point is, how do we compute the constant ductility spectra from the data that we used for our ductility demand spectra. And it's pretty straightforward. There's two ways that you can do this. It's kind of like, computing an intersect, okay? You use the bisection method, right? When we're trying to find something, and it is a trial and error kind of problem, right? I guess one thing, I correct, I go, oh, maybe I went too far, I go back and forth, and you can do all that. The other way to do it is you can create a database. You can run it for, which is what's on the left-hand side, you can run it for a whole lot of R factors or Fy strengths. And then, so if instead of having just 3 curves, I have 100 curves, then you can literally interpolate, just as if you're trying to find an intersect. If you just compute all the reasonable values, of course you have to stay in a range, you can find your intersect just by finding in your data set, what point intersects your line. So you could do it 2 ways. One, you can do it iterative, which could be faster, but it requires a lot more algorithm around it. Or you can just create a large data set, a database of these curves on the left, and then just interpolate between these 2 lines. Let's say you want to reach a ductility level of 5. Well, here I can find out at whatever this period here is. And so then I know that my RY factor needs to be somewhere between 4 and 8 to achieve that ductility level. And so you could do it both ways. So if I have a lot of lines here, if I compute it for, and this is the way I like to do it, just because I want to create the plot on the left and the one on the right. And computer power is cheap these days, and storing the data. So sometimes it's just easier to just create a large database of these and then interpolate these lines to just replot them into these curves. And so when you go through these interpolations, you will find that some of these lines will cross. And I believe you either choose the highest or the lowest F value. And so you could still do it, through iteration, or you could through the data set, and you add an additional algorithm if you have more than one solution. It's very tricky whenever somebody talks about an R factor. Make sure that, and this was something I mentioned early on, the terminology is very important. In any one of these definitions, make sure that you either make clear what definition you're using, or if you're communicating with somebody, make sure you're on the same definition. The other thing to keep in mind is the effects of damping and yielding. Again, this comes from Chopra, and it's something to think about when you're building your model, what damping ratio you're gonna use. When we have an elastic system, we put in 5% damping, which is also meant to represent energy dissipation. And so when you're going into your modeling the yielding explicitly, then the recommendation is to drop your damping ratio. And it's interesting because oftentimes, and that's really the highlight of this sentence, and this is just a lot of text that's interesting from Chopra's book, and it'd be great, I recommend going to read about it, is that damping comes into play right here in the middle region. In longer period systems, there isn't, you've got large deformations, and therefore it's really your hysteretic damping, as well as in your short period. And so damping is really important in this middle range. And so don't disregard it, but it's important. But, even going from 2 and you're doubling to 5 to 10% damping, your changes are only 5 to 10% in response, which is something, or actually no, because this is logarithmic. So it's important. And the moral of the story is kind of cool, is that Chopra is saying, and is making the point, is you've got to take into account damping, and it's not so easy. We can't represent hysteretic damping through viscous damping. And so make sure that you're considering both viscous damping to represent viscous damping and hysteretic damping that you're modeling explicitly in your model. And what kind of hysteresis does your model have? The point of it is here, and it's really the point that I'm making through today's presentation, is even damping is important. Everything, all the different decisions are important, and you want to evaluate what are the effects on each one? It really depends on your ground motions. It depends on your case. It depends on what you're trying to do. Another application in 2010, Professor Bozorgnia with Mahmoud Hachem and Kent Campbell. I didn't know that Kent Campbell was part of this. So they took the NGA West 1 record and ran a large and built a huge database of inelastic spectra. And that's why I recommend going on the database and then interpolating that data to get to the ductility levels, because then you have that much more data to really play with in the post-processing. And so it's kind of cool because this was the first step towards inelastic design spectra. I focused on elastic response spectra, but this work is actually heading in the direction of developing inelastic design spectra. And so it's kind of neat that they've developed these predictive curves, and this is just like the NGA GMPEs, right? A magnitude term, distance term, a fault types, and all the different same characteristics that you have for the NGA West 2 models, but actually for different levels of depending on magnitude, or here's your constant ductility spectra, where now on the vertical axis is Fy is a function of W over W here. So always read what's on the y-axis, okay? Because it's often different, and make sure that you have the definitions there. And in this case, they actually did use 5% damping, for example, in the database because they were running the whole range. And so you don't want to have discontinuities when you go from R factor of 1 to 1.5 to 2.